Alright, what's up guys? In this video, we're going to pick up with some calculus here, and we're going to complete the integration exam number 1 for calculus. So we got 5 examples that we're going to go through, and I'm going to show you how to evaluate all these integrals and explain the process for each thoroughly. So if you have any questions about it, feel free to ask me at any time. So without wasting too much time, we'll go ahead and get started with number 1. So that's to evaluate the integral e to the 3x multiplied by sine of e to the x dx. So the first thing that we can do here, obviously, is a simple u substitution. And we know that the derivative of the exponential e to the x is just itself. So that'll help us cancel some stuff out. So we'll get du is equal to e to the x dx if we take the derivative of it. And then we get 1 over e to the x. Du is equal to dx because we need to solve for the dx part. And then just to kind of illustrate what happens over here, we have e raised to the 3x multiplied by sine of u. Now remember down here when we solve for the dx part that we have e to the x being divided by our 1 here, but remember that u was e to the x, so we can replace that e to the x with the u. So this would be 1 over u, and then we got du. And if you simplify this, this would just end up becoming e to the 3x multiplied by sine of u all over u integrated with respect to u. Now you're probably wondering, what can we do here? Because notice that we have e to the 3x sitting in here. We've changed the variable to a u, so that's going to create a bit of a problem. And in some cases, if you end up getting in a situation like this and you can't get this x in terms of u, then you probably picked the wrong technique and you need to try another one. But in some cases, if it comes up like this, you can still get this in terms of the new variable. In this case, we can, because remember that u was e to the x. So what we can do is take the natural logarithm of both sides. So we'll get ln of u is equal to the natural logarithm of e to the x. We know that ln of e to the x is just x, so this will give us x is equal to ln of u. So what we can do now is replace what we have. So we'll have we'll have e raised to the 3 ln of u multiplied by sine of u all divided by u being integrated with respect to u. So now we have everything in terms of u like we want. Now we can clean this up. Remember, e to the 3 ln of u, that's just going to be u to the 3rd if we think about our exponential rules. And so then we would essentially have u to the 3rd times sine of u all divided by u. So we'll have u to the 3rd multiplied by sine of u all divided by u, which will essentially, if we divide that u cubed by a u, we'll simply get the integral u squared times sine of u du. And again, you can shorthand most of this extra work that I'm doing. I'm just kind of doing all the extra work and showing you the extra steps, all this stuff like that for the purposes of the video. But if you're actually doing this in a class setting, you can shorthand a lot of this stuff and you can do it, most of it in your head, and you won't have to write down all of this. So I just want to make you aware of that. So this is the integral that we have arrived at now that we've done our initial substitution. So what do we do next? So as you can see here, we have a product of 2 different functions. So we're going to need to use integration by parts here. Now notice, we're going to have to use integration by parts twice, because notice that we have u squared times sine of u du. Well, once we do integration by parts the first time, it's just going to reduce the power of the u down to 1, and we're going to have to do it again. And you'll see this once we get through kind of a bit of the process. So I'm going to abbreviate the integration by parts with IBP apostrophe S instead of writing the whole name down. And remember, the formula for that is the integral of u dv is equal to uv minus the integral of v du. You just get that from the product rule if you integrate both sides of the product rule. We need a u and we need a dv. So u here, I'm just going to pick it to be u squared. And then that means that dv is everything else. So dv will be sine of u du. Then we find du is 2u. And then v will be the antiderivative of the dv, which is sine of u du. And we know that the antiderivative of sine of u du is negative cosine of u. You don't have to add a plus c there. We're going to add a plus c at the end. You don't need to put it there when we're doing our initial integration by parts. And let me get another sheet. And as you're going to see, once we've done our integration by parts the first time for this, we're actually going to have to do it again. And you'll see this in a minute once we set everything up. So over on this side, we'll have minus u squared multiplied by cosine of u. All I did was bring the negative to the front. We would essentially have two negatives, which would make it a positive, and I'm going to pull the 2 out front. And then we'll have the integral of u times cosine of u du. And the new integral that we're going to deal with now is the integral u times cosine of u du. Now, if you notice here, we have a product of two different functions again, so we're going to have to apply integration by parts again. But you guys already knew we were going to have to do that again based on what I told you before. A quick way to identify whether or not you're going to have to do it twice, sometimes you have to do it 3 times. If you see something like this, let's say x squared times e to the x dx, for example, that'll require integration by parts twice. If you see something like ln squared of x dx, that will also require integration by parts twice to integrate, because we know to excuse me, to integrate ln of x, we would have to apply integration by parts. So to integrate ln squared of x dx, we would have to do it twice. So just keep that in mind. So we're going to do our integration by parts again, and we're not going to change anything up in terms of the selections. We're pretty much going to stay very similar to what we had for the first ones. And we go through the whole thing. And then v here, du is du. And then v here is going to be the antiderivative of our dv, which is cosine of u du, which we know is obviously the positive sign of u. Again, we're going to put a plus c at the end, so don't worry about the plus c right now. Remember the 2 that was pulled out front earlier? Where did I pull it at? Oh, I'm sorry, it's up here. So remember I pulled the 2 out earlier. Just to kind of remind myself that it's still there. I'm going to, bring it on the outside there. And it's positive, so that's the reason I'm going to do it. And then we'll just have u times sine of u minus the antiderivative of sine of u du, which we know is negative cosine of u, but we're going to go through the whole process. And since we know that it's going to be negative cosine of u, and we know we already have a minus sign there, that's going to be 2 minuses, which is going to equate to a plus. So we'll have 2 times u times sine of u plus cosine of u. And when we do our second integration by parts, this is what we would get for that one. Now, when you're doing integration by parts and you have to do it multiple times, it is very important that you make sure you're being very neat. Because notice here how everything is nice and neat. When we did our first integration by parts, notice how everything is very organized. The reason why you want to do this is because once you've done your initial integration by parts, you're going to have to go back to the first one that you did on the left-hand side. Because remember, the side where we do our u times v, we don't really touch that at all. We're just integrating that side, the v du part. You will have to go back to the left-hand side that was before the integral in the formula and actually attach it to whatever you got when you did it the second time. So if you have stuff all over the paper and it's not organized, then it's not going to be good. So make sure you're being nice and neat on that, kind of like what we did here when we did our new, oh, by the way, sorry, it's du. So now we're going to take our, what we got for the first one, which again was up here, and we're going to attach it. So this would be negative u squared multiplied by cosine of u. Remember, this was a positive 2 because we ended up getting that. And then this was u times sine of u plus cosine of u. So that's what we get when we actually attach the first integration by parts, we actually used 3 different techniques in here. I didn't actually realize that until I just got done talking about it here. We did a U substitution to initially start, and then we did integration by parts. Okay, so now all we have to do is plug the U back in. So remember what U was. U was e to the x. So to get our final answer, all we really have to do is just plug that stuff back in, and that'll give us our answer, and we can write that all out. So the final answer for this integral here, we're asked to integrate e to the 3x multiplied by sine of e to the x, all integrated with respect to x. And the answer to this is negative e to the 2x cosine of e to the x. I'm sticking in e to the x for all those u's. Then this would be plus 2e to the x multiplied by sine of e to the x plus another 2 cosine of e to the x plus c. So the answer here is relatively long. And by the way, I went ahead and expanded out by distributing in the 2 and then putting in u is equal to e to the x. So that would be the answer. So the answer is a little long, but that's just life. That's just math life, I guess. So sometimes the answers will look a little long and may look ridiculous, but that doesn't mean it's not the solution just because it looks a little funny. So if you've done everything right and you're pretty confident on your calculations, then how it looks shouldn't bother you at all. The solution, that is. So that was number 1. So maybe that one was a little bit involved. But I think we went through it pretty decently. And again, you'll probably move through most of these questions quite easily during an actual class than you see me doing on video, because I'm trying to just show you guys how to do it. Okay, so now we're going to move on to number 2. We're going to do 5 of them, by the way, like I said at the beginning of the video. So this would be number 2 for us, another indefinite one. We do have some definite ones in here. I think I did 3 indefinite ones and 2 definite ones, but I gotta go through and let's see. So we're gonna do this next one here. So you get the integral of e to the x all over 4 e to the x plus 6 integrated with respect to x. Okay, so all we really need to do for this one is also a u substitution. Again, we just pick u to be 4 e to the x plus 6. And then du here is obviously just going to be 4 e to the x multiplied by dx. Then we'll have 1 over 4 e to the x du is equal to dx. The e to the x's will cancel out. You can take out a 1/4, which is just a constant. And then when the e to the x's cancel out, you'll just be left with 1 over u du in our integrand here. We know that the antiderivative of 1 over u du is just a natural logarithm of u, absolute value. So, and if we apply the constant multiple rule, then this will essentially just give us 1 over 4 ln absolute value of u, technically plus c, if you want to be technical with it. Now, key thing to keep in mind with these natural logarithms, a lot of students get in the habit of doing this, and I was guilty of doing this myself. You can't just take these absolute value bars off the natural logarithm anytime you want to. They're absolutely necessary in most cases, and so make sure you keep them up unless you absolutely know you can take them off. For most definite integrals, especially if the limits are positive, you can take them off. And so there are some cases where they can be dropped, but you can't just take them off anytime you want to. So make sure you leave them up when they're absolutely need to be left up. And I always look at it like, if you leave them up when you could have took them off, that's not a bad thing. But if you took them off when you should have left them up, that's the bad thing about it. So you won't be penalized for leaving them up if you could have took them off, but you'll certainly be penalized if you take them off and you should have left them up. So just keep that in mind. And then pretty much all you have to do to finish this up is you take your u, which was 4 e to the x plus 6, and you just put it back in for u. And that would be how you solve it. So the final answer for this one, we were asked to deal with the integral e to the x all over 4 e to the x plus 6. And that was all being integrated with respect to x. And our answer to this is just going to be 1 over 4 ln absolute value of whatever that is. That's 4 e to the x plus 6. And then we do need to add that integration constant at the end. So that would be the answer to number 2. So perhaps that should have been number 1, because that was a little easier than maybe the first one that we did. I don't think the first one that we did was too hard. I just think it was a little lengthy. And some integrals can be like that. They can be long, but not necessarily difficult. Like when I showed you guys at the beginning when we wanted to integrate, just as a feedback. Remember when we were talking about the different situations where you may have to apply integration by parts twice? If we look at something like this, integrating something like that is not hard, but it is lengthy. So there's a difference between an integral that's hard and one that's just going to take a little bit of time to get the answer to. So that was number 2. So we're going to move on. All right, let's get the next one here. I got some extra sheet over here, by the way, as well, if we need it. We're on to number 3, so we're actually moving at a relatively decent pace. Okay, so what about number 3? So we got the integral cosine cubed of 20x dx. So this is a trig integral. So obviously all we really need to do is just a u substitution to start. So u would be 20x, du is 20 dx because you take the derivative. We get 1 over 20 du is equal to dx. So what that means is 1 over 20 will come out front because that's just a constant. And then we'll just have the antiderivative of cosine cubed of u all integrated with respect to u. Now, cosine cubed of u, that's the same thing as cosine squared of u multiplied by cosine of u, because although you may not see it, this cosine is being raised to the first power. Cosine of u raised to the first power is just cosine of u. So this is approximately equivalent to that. The reason why we want to break it up is because if you remember the Pythagorean identity that sine squared of theta plus cosine squared of theta is equal to 1, if we wanted to solve it for the cosine squared theta, or in our case u, since that's the variable we're using, we'll simply have cosine squared of u is going to be equal to 1 minus sine squared of u. So we can actually replace the integral here, or the integrand here, to make it easier to deal with, because initially we don't know an initial antiderivative for that. And we also don't know how, we also can't apply any particular integration technique to this right off the rip. So that's the purpose of actually going through and doing it, breaking it up like that. So the 1 over 20, that was pulled out. And so now we got cosine of u multiplied by 1 minus sine squared of u. And that's all being integrated with respect to u. So now we've got the integral in a form now where we can actually deal with it, and we can do another substitution. So the best thing to do here would be to pick your next substitution. I would pick sine of u to be the next substitution. By the way, if you need to do another substitution, this will happen with some integrals, you need to use a different variable than a u, okay? You need to use a different one. It doesn't really make a difference what variable you use. If you need to do a second substitution, you use any letter of the alphabet for all I care. But as long as you're going about the process the same way, it doesn't matter what variable you use. Typically, when people have to do another substitution, they'll use v. I kind of like to go a little unconventional and just be a little different. I'm going to use w. Again, it doesn't matter what variable you choose to use for your second substitution, as long as you are following the general premise. So in this case, I'm going to pick w to be sine of u, and then that means that dw is cosine of u du. Then we'll get 1 over cosine of u dw is equal to du, because we had to solve for the du part. And so we got our 1 over 20 that was out there. Remember, we didn't do anything with that. And then once we actually substituted everything in, the cosines of u would cancel out, because there would be 1 here, it would cancel out with that one. And so on the inside, we would just be left with 1 minus w squared, all integrated with respect to w. So this is approximately equivalent to 1 over 20 times the integral of 1 dw minus the integral of w squared dw if you apply the difference rule for integrals. And we know that this would just end up giving us 1 over 20 when we integrate we know that that's just going to be w plus w cubed over 3 if we actually use the power rule for integrals. And so to finish this up, all we have to do is substitute back in for u and for w. And this is another reason why you want to be nice and neat, so that way you don't get lost with what you had. So remember what u was. U was 20x. And the second substitution, we chose w as the variable to use. That was just sine of u. So all we have to do is plug that stuff back in and write down our final answer. Okay, so what's going to be our answer here? And I'm going to kind of distribute as well and kind of kill two birds with one stone. So we're asked to integrate cosine cubed of 20x dx. So our answer in this case is just going to end up being 1 over 20. And we have to stick back in our u and we have to stick back in our w, which was the substitutions that we initially did. So this would be 1 over 20 sine of 20x minus 1 over 60, because remember that 20 times 3 is 60. And then it would be sine cubed of 20x. And then we have to add a integration constant to the end to give us our final answer. So that would be the answer for number 3. So let me circle that for you guys. And that's basically how you solve that one. So as you can see, it wasn't too bad going through this one. You did need to use a trig identity in there, but it wasn't too bad. It wasn't too difficult. So that was number 3. Okay, so I think we're moving relatively at a decent pace here with these. So that was number 3. All right, let's get our next one going here. And I'm also going to post a video with the trigonometric integrals example that we're going to do. I'll post a video for those too. So now we're down on to number 4, and we're moving at a pretty decent pace here. Okay, so we're now on some definite integrals here. So we got the integral here from 2 to infinity. We got dx over the square root of x that we need to integrate. Okay, so this is what's called an improper integral. So let me remind you of what an improper integral is and how you deal with these, because it's a little different than just some other integral. So improper integral is basically a specific type of definite integral where you either have infinity as a one or both of the limits of integration. And sometimes infinity can be negative as one of those limits. And you can't evaluate an improper integral the way that you could some other integral with finite limits, because infinity is not a real number. It's infinity. I always kind of like to say it when I try to explain to students about limits. Infinity is not a value. It's more of a concept. It's more of a it's not a value. I don't know how to explain it. It's not, so you can't just plug. It's kind of like when you're taking limits, if you remember from calculus 1, when you take limits at infinity, you're not technically subbing in infinity because it's not finite, right? You have to look at the behavior. So basically what you do for an improper integral is, to solve it, you have to replace the infinity with some variable. Typically t is used, but some books do use b, but it doesn't really make a difference. Some books use b, some books use t, but you typically replace the infinity sign with a variable, which is typically t, and you evaluate the integral that way, but you have to take the limit of the result. So if I have an integral, for example, from a to infinity, for example, of some function, and I want to integrate that with respect to x, basically what I do is I take the limit, and as t goes to infinity, and what you do is you replace the infinity with a variable, typically t, and then you get f of x dx. And now you can evaluate the integral, because by just using part 2 of the fundamental theorem of calculus, but you can't just sub infinity in. So make sure you keep that in mind about improper integrals. And I do have some videos on them, but not very many, so I'll try to post some a little bit later. So this a here could be any value. Sometimes it'll be 0. In our case, it's 2, but it could be anything, and depending on the circumstances. And so this is the integral that we're given, and we need to convert this now. So this becomes the limit as t goes to infinity. And now we just take our infinity there and we replace it with the t, and then we integrate this dx over the square root of x. First thing that you should remember, and I'll do it over here. Well, actually, I'll write it this way. Remember that, well, actually, no, I'll write it down here because I want to show you the. So let's just say I have the integral of 1 over the square root of x to be integrated with respect to x. Well, we know that you can write the square root of x as x raised to the positive 1/2. So essentially, this integral is approximately equivalent to 1 over x raised to the 1/2, all integrated with respect to x. But to get rid of that fraction almost, you can move this x to the negative 1/2 up front, and then the integral essentially becomes x raised to the, or x raised to the positive 1/2, you move it up front, it becomes x raised to the negative 1/2 dx. If you actually rewrite and then move the x to the 1/2 up top to get rid of the fraction. And so a lot of times with these integrals, maybe not necessarily, well, maybe for this example, obviously, but you can use a little bit of algebra to rewrite it and turn it into an integral that you actually do recognize and how to deal with. But hopefully by the time you get to Calc 2, which is when you start learning about improper integrals, you'll already know what the integral of dx over the square root of x is. But just in case you didn't, I just wanted to point that out. Okay, so what we'll have is the limit as t goes to infinity. I went a bit off topic there, so I apologize. But when we integrate that, let's say I go ahead and convert it to x raised to the negative 1/2. Well, if we integrate that, we know that negative 1/2 plus 1 is positive 1/2. So if we actually integrated, it would be 2 times x raised to the positive 1/2, evaluated from, what was it, from 2 to t. And then we take the limit. Now, keep in mind, the limit as t goes to infinity, it'd be 2 times the square root of x, all evaluated from 2 to t, is the exact same thing as this, because we know that x, or the square root of x, can be written as x raised to the positive 1/2. So this is approximately the same thing as this is. So that's kind of what makes this stuff a little difficult for a lot of students without actually knowing the algebra and knowing that, you know, these expressions are approximately equivalent to each other. And now we can apply the fundamental theorem of calculus and actually go through and do it now. So we sub in the t first, and then we sub in the 2 after that. So it looks like we'll get the limit as t goes to infinity for 2 times the square root of t minus 2 times the square root of 2. And we take the limit. Okay. Well, this is just going to give us infinity. So this improper integral is going to diverge, by the way. It's not going to converge because we're getting infinity when we take the limit here. We're just going to get, so if I take the limit as t goes to infinity for 2 times the square root of t, that gives me infinity. The limit as t goes to infinity for 2 times the square root of 2, it's just 2 times the square root of 2. So this would be infinity minus 2 times the square root of 2, which is just infinity. So this integral is divergent. So we should have actually wrote up here, state whether it's convergent or divergent. Since we did not get a finite value, infinity is not finite, this is a divergent integral. So your final answer for this one is, we can, when we evaluate it, we just simply state that it diverges because we end up getting infinity. So for an improper integral, sometimes you'll get a finite value out when you integrate it, and if you do, then obviously the integral converges. But if you get something out like infinity after you've taken the limit, then it just diverges, so it doesn't converge at all. So this is a divergent integral because we get infinity. So that's number 4. So I'm going to do a video on improper integrals. I haven't done very many on them, but they're definitely integrals that you want to be familiar with. Again, you'll learn about these in Calculus 2, so they won't jump out at you until then. Because obviously you don't really start the concepts of learning definite integration until Calculus 2 anyway. So You have to wait to get to Calc 2 before you actually start dealing with these. Okay. Also, one other thing I wanted to mention about the improper integral. An integral can be still considered improper even if the limits are finite. If it has a integrand that's discontinuous on the interval of integration, it can be considered improper as well. Now, those are a little bit more difficult to spot, but typically, if you see infinity in there as one of the upper or lower bounds, most times it's the upper one, but obviously it could be the lower one, and sometimes you can have infinity. Let's say you could have negative infinity here, positive infinity there. In that case, you have to break the integral up into two pieces in a case like that, which I've done videos on that before and evaluate it that way. But it can still be considered improper if it's discontinuous on the interval of integration, even if it has finite limits. So those are a little bit harder to spot. So that's number 4. So we're actually moving at a relatively decent pace. So let's get number 5 going here. And I think we're doing pretty good. So this is our last one, and we need to evaluate this. So how do you evaluate the integral from 0 to ln of 2? We got x times e to the x dx. So we have a product of two different functions, so we're of course going to use integration by parts for this. And you use integration by parts when you have a product of two different functions. We have an x times an exponential function e to the x. The formula for integration by parts is the integral of u dv is equal to uv minus the integral of v du. If you integrate both sides of the product rule from first semester calculus, you get that. We need to identify what u is and what dv is. In this particular case, neither of these is harder to differentiate or integrate than the other, but I'm going to pick u to be x, and that means that dv is everything else. So dv is going to be e to the x dx. And then we just go through the meticulous process that we always go through of taking our derivative here, derivative of x is dx, and then we get v is equal to the integral of e to the x dx, which you know is just e to the x. Okay. So now we use our integration by parts formula. And I'm going to write this side as e to the x multiplied by x. Remember, multiplication is commutative, so it doesn't really make a difference how you write it over on that side. You can kind of clean it up, make it look nice. And then this will be minus the integral of e to the x dx. This is where we're at. Now we know that the antiderivative of e to the x dx is just e to the x. So, and this is evaluated, by the way, from 0 to ln of 2. So essentially what we got is e to the x multiplied by x minus e to the x. And again, it's evaluated from 0 to ln of 2. You sub in your upper limit first and your lower one. So we use the fundamental theorem of calculus. So we'll get e raised to the ln of 2 multiplied by ln of 2 minus e raised to the ln of 2. And we see what we get when we plug that in. Well, we're just going to get 2 multiplied by, it's going to be 2 ln of 2 because e to the ln of 2 is just 2, but we're multiplying by ln of 2. And the same thing over here, so this should just end up being minus 2. Then when we sub in the 0, remember that e to the 0 is 1, so this would be minus, so that means we'll get negative 1. So this essentially becomes plus 1, and we'll just have negative 2 plus 1. And so it actually just come out to being 2 ln of 2 minus 1. And that would actually be the answer. So your final answer for this integral here, and this one was, I guess, a little easy, is going to be that 2 ln of 2 minus 1. So we're asked to integrate from 0 to ln of 2, we were asked to integrate x times e to the x dx, and the answer to this is 2 ln of 2 subtract 1. What that is in the calculator, you can obviously just type it in right quick if you want to and see what it is. So it's 2 ln of 2 minus 1. That's 0.386. I guess if you want to write, you don't have to do this, by the way, but so it looks like we'll get 0.386. And so again, if you want to write as a decimal you can, but you don't have to. And that would actually be the answer for number 5. So that is going to complete or conclude the integration exam number 1 for calculus, where we went through and actually did a bunch of problems and evaluated integrals, and that's actually going to be it for our test today. Okay, so hopefully I was able to clear up any questions that you may have about these types of problems. Again, the way that I got better at evaluating a lot of these integrals is by doing a bunch of practice problems, and that's really the only way that you're going to get better at it. And so I just encourage you to work on problems on your own at home during free time. And don't be afraid to ask questions. I always say if you're not asking questions in any math class, not just calculus, then there's something wrong. Because not even myself, I didn't understand this stuff right off the rip. It's going to take a little bit of time. So stick with it and don't give up. So that's integration exam number 1. So we'll have another integration exam number 2 coming up sometime next week. And you guys can view that one as well. All right, so that's going to be it, guys. I'll see y'all next time, and thank you for joining.